Yo, John. Should have came over. We're gonna do Sudoku. Sudoku solver. Yo, John. Should have came over. Okay, what's up, everybody? Today I'm gonna work through this problem called, or I had a subscriber talk about any tips on matrix problems, 2D arrays. They couldn't seem to get down things like Sudoku and spiral matrix. Spiral matrix, they commented it's on my diagonally traverse question. And spiral matrix is this other one. I've seen this question before. But I'll work through this one if I have time. I have like a pretty unique solution for this. But let's just get into any tips for matrix problems and 2D arrays. So help people out with that. So pretty much when you're working with 2D arrays in Python, everyone's familiar with 1D arrays like 1, 2, 3, 4, 5, right? So this is an array of length 5. So if we want to do a 2D array, essentially what we need to do is create an array that captures this array. So 2D arrays are arrays that contain other arrays. So pretend we have this one array. What we do is we'd wrap it in another array and take like the inside here. So this would be, I'll show you what a 5 by 5 array looks like. So this is what a 5 by 5 array would look like. It's basically an array of arrays. So you see the 0th element. This is the 0th element. That's an array. How's the Xmas party? That's good. Team bonding. Come over though and see the fam. But essentially, this is a 0th element, and every element in a 2D array is an array itself. So the 0th element is an array of length 5. The first element is an array of length 5 as well, and this whole array has 5 lengths. So to get the number of rows of a 2D matrix, usually you just take pretend this is the matrix. Matrix also a 2D array. To get the number of rows of a matrix, usually you do this. You take the length of the matrix. So when you take the length of the matrix, that gives you the number of rows in the 2D matrix. And to grab the columns, and the reason that works is because taking the length gives you how many indices are here. So, and then in order to get the columns, usually you go like this. Columns equals length of matrix. And usually I just grab the 0th element. So that's essentially what that code is doing, is it's capturing the 0th element, and then it's taking the length of one of the arrays here. So are you lit right now? So essentially, yeah. Okay, cool. What time is your flight? Dude, my YouTube stats have been tanking without you, man. All-time lows right now. What's it called? But let's get back into this. So the number of rows equals the length of the matrix. So that's how much indices are here. And then the columns is, we just grab one specific thing. So that's usually all that I care about. And then pretend a lot of the times what we care about is if we're given a certain element, we want to grab the neighbors right here with the extra comma. No, that's how you define a 2D array. You're good without the commas there. But a lot of times in a 2D matrix, you want to grab the neighbors. So usually to grab the neighbors, logic that you do is, so pretend I want to grab the neighbors of a specific row and column, and that's given to me as a tuple. So for in this case, say that we're at this middle one, so that's 0, 1, 2. The row is 2. So pretend we're at row 2. And I should have 0 indexed these. Should have went like that. So we can refer to this. So what are we gonna do? So for this one, the row is 0, 1, 2, and the column is 3. So a lot of times when it comes to these matrix problems, we want to be able to grab the neighbors. So the quick way to do that, and you'll see a lot of people do it, is they'll take pretend I'm giving row and column 2 and 3. What I'll do, okay, cool, I'll drive you. I'll take the row and column, and to grab the column above us, we'll take the current row we're at and we'll -1, but we'll stay in the same column. To move 1 to the right, what we'll do is we'll stay on the current row we're at, right? We'll stay in the current row we're at, but we'll increase the column. To grab the neighbor below us, we'll increase our row. That'll get us to row 3, and we'll keep the column the same. So we'll go row +1. We'll take our column, and we'll stay in the same column. John, are you dropping a video today? Lastly, we'll stay in the same row, but we'll -1 from the column to get there. So we'll stay on the same row, and we'll minus a lot, or we'll minus from the column. So that's how you get the neighbors. If you want to grab this neighbor, you can -1 from the row and plus to the column. If you want to grab this neighbor, you can minus from a column and minus from a row. If you want to grab this neighbor, you can plus to a row and minus from a column. And this one, if you want to plus to a row and plus to a column. So those are the different ways that you can grab the neighbors. And you need to watch out for if you're trying to grab the neighbors and you're in a corner, or you're at the bottom, or you're at any of the edges. So a lot of times for the neighbors, we're gonna do bounds checking within, like, for when we're looping through the neighbors, we're also gonna do bounds checking before we access the matrix. So yeah, those are the main things that we need to worry about, that I think about when working with matrices. So I think those are mostly my tips, and I'll show how I would solve Sudoku. So determine if a 9x9 Sudoku board is valid. Only the filled cells need to be validated according to the rules. So each row must contain the digits 1 to 9. I recognize this from the back propagation code. Oh, okay, I see. So let's see. Determine if a 9x9 matrix is valid. Only the filled cells need to be validated according to the following rules. John, are you going to drop any content today? So each row must contain the digits 1 to 9. So these rows, nice. Can't wait. So each row must contain the digits between 1 to 9. Each column must contain the digits 1 to 9 without repetition. And then each of the 9 3x3 sub boxes of the grid must contain the digits 1 to 9 without repetition. A Sudoku board partially filled could be valid, but is not necessarily solvable. Only the filled cells need to be validated according to the mentioned rules. So we're not trying to fill out the Sudoku. That's what I'm going to work on next. But in order to fill out a Sudoku board properly, because this next problem wants us to find a Sudoku solution, we need to perform like a backtracking algorithm that will try out all the different possibilities of solving the Sudoku puzzle. And if it ever runs into a state where the board is invalid, it should backtrack. So I need to be able to solve this valid Sudoku problem as well. So what I'm going to do for that is I'm going to figure out. So what I basically need to like parse this whole 2D matrix and then check all of that all of these rules are like work. Basically each row is 1 to 9 without repetition. Each column must contain digits 1 to 9. So let's just work slowly through this by first working on every single row and then making sure all the rows are good. So we'll add logic called rows my water. So each row must contain the digits 1 to 9. Without repetition. Wait, is this true? Right here? Yeah, this board is true because it doesn't break the constraint. Same except with 5 in the top left corner. Where is this? Why is this one false? They didn't even give a good example. Same as except with the 5 in the top left corner being modified to 8. So why is this breaking? 8, 8. Since there are 2 8s in the top left sub box. Okay, I see. So essentially what they did to make this not work anymore is convert this 8 to an 8. And now since this sub box is an 8, has 2 8s, it no longer works. So what I'm going to do is, let me grab the Sudoku board. First, my first step is I'm going to validate rows. So to validate rows, what I'm going to do is I'm going to loop through every single row and grab a set of all of the elements in that row. While if I essentially want to just check uniqueness in every single row independently of all the other rows. So I just need to make sure there's no collisions in this row, no collisions in this row, no collisions in that. And the best way to do that is with a set. So what I'm going to do is I'm going to loop through every single row. And like I mentioned, every element in the board is a row. So we'll go look over rows. So I'll say for row in board. So it's pretty much going to be looping through each of these elements, and each element is a row. So for row in board, I'm going to validate uniqueness. So I'll create a function called validate uniqueness self. And for that, I'll give it in a, I mean, we probably don't need a function for this. We'll see. So for row in board, and I'll loop through every column in that row for column in row. And then I'll have a unique nums. And this will be a set. And then I'll say, now when I access each of these elements, I need to pass in, well, I already have the row, and I'm just grabbing an element in the column. So let's just say, how would I do this? Let's just use, yeah, so this is grabbing every, let's just call this column element. And then, so the first element here will be 5. So if column element is in unique nums, we automatically return false. Else we'll add unique nums dot add, and then we'll add the column element. So it'll do that for every single row. So for every row, it's going to loop through the column and check for uniqueness. After it moves on to the next row, it's going to ditch this unique nums, and it will look at the next row sort of independently. So that helps us look over the rows. Now let's look over the columns. So for columns, like I mentioned before, to grab the length of the columns or to loop over the columns, yeah, we're going to have to verify. Sorry, let me close this out. What the logic is doing is we're going to have to verify each row. And then after we verify each row, we got to start verifying each column. And then after we verify each column, we need to verify each of these like independently. And if all of those are valid, the whole Sudoku puzzle is currently valid. It doesn't need to be filled out to be valid. It just needs to, they just want to know is like if the current state is valid. So to look over columns, like I mentioned before, to loop over the columns of a matrix, you take the length of one of the rows. So if I take the length of the 0th element, it'll give me this. It'll give me 0, 1, or 1, 2, 3, 4, 5, 6 there. So I'll say for column in the range of the length. So we'll take a row and we'll take the length of one of the rows. Mods in the building. What's up? What's up? I'm going to be solving Sudoku for one of my subscribers. And then maybe I'll look at this thing if it's not too hard. Oh, it doesn't even look that hard. Wait, see, doing this. Some math problem. Let's see. So we're validating the rows for column in the length of the board. We're gonna verify each column, and then we're also gonna loop through the rows for row in range length of board. So we're gonna loop through each column. We're gonna go column by column, and for each column, we're gonna verify all the rows are unique. So we'll use this unique set, and then we'll say now we're using indices. So now that we're using indices, we're going to access specific indices in the did you finish the last advent? Nah, I didn't run it, but one of the subscribers gave a good piece of code that probably would have worked, but I didn't get the chance. Today I'm solving this. One of the subscribers asked to get advice on how to work with matrix problems in 2D arrays. So I'm doing Sudoku specifically before I get into that. And if you're just joining in, basically I was just showing what a 2D matrix looks like. It's basically an array of arrays where each element is an array. So to grab the rows of the matrix, you just take the length of the matrix. To grab the columns, you just take any element. Usually I grab the 0th element of the array, and then I take the length of the 0th element to grab the columns. And then I also showed the code for how to grab the neighbors of, like, a lot of times with these array questions, we just want to grab the neighbors. So I showed how you can like -1 and +1 from the specific row and column that you're at in order to access the different neighbors. And pretty much all you need to care about, or like one thing that you need to care about, otherwise your code will just crash, is pretty much when you're on the edges, you have to do a bunch of balance checks and stuff like that. Let's see. Now I'm just validating the Sudoku. So I'm validating all the columns and checking for uniqueness. So let's say grab the element, and we're given the board, and we're gonna grab the row. The row is always the first or when you access the array, it's always the first bracket thing here. So we grab that element, and we say if element in unique nums return false, otherwise we add that. So we say we grab the element, we check if the element is in the unique numbers, and then if it's in the unique numbers, then we return false, because we're just verifying uniqueness in a specific column. Otherwise we add it there. So let's just run that now. So now we're looking over the columns. That's true. We're looking over the rows, we're looking over the columns. Now we need to do this last check of checking each of the sub boxes and making sure there's no repetition in those sub boxes. And if all of these check out to be true, we'll just return true. So we'll be like check sub boxes. So how I usually do this is to grab a sub box. Since what we'll do is we'll take the index of whatever row we're at and then do a mod of probably a mod. Let's see. Because this, let's say this is supposed to be 0, 0. Like what I'm trying to do is assign like tuples to each of the sub boxes so that I can group certain rows and columns into a specific, so I can group them in the same group, the same way I'm grouping And then I could verify elements in the same group against each other the same way I could verify rows against each other. So I would want this group to be called 0, 0. I want this group to be 0, 1. This group to be 0, 2. This group to be 1, 0. So how I'm gonna do that? Let's see. For this one, is a set fine? You'll need to use a hash map. So John, hash maps and sets are the exact same thing under the hood. Or like dictionaries and sets are exact same thing under the hood. The main difference in Python is when you create a dictionary, usually you're storing some sort of key value pair. But if you don't care about any value, you can just create a set, which pretty much just stores like a bunch of values or keys or whatever. But under the hood, they're both using hash maps. So what am I gonna do? I think, let's say this is row 0, 1, 2, 3, 4, 5. I think if I take the row and do like a integer division by 3, I'll get what I want. Because what's 0 divided by 3? 0. 1 divided by 3, 0. 2 divided by 3, 0. 3 divided by 3, 1. 4 divided by 3, 1. And this is like a integer, or this is the integer division. 6 divided by 3, then we finally get to 2. I was thinking of doing an enumerate. But I think if we just take the row and divide it by 3, we can properly capture the row here. So it'll properly increment. So we'll get something like this. And then even with the columns, if we just do, pretend it's 0, 1, 2, 3, 4, 5. So what's 5 or divided by 3 integer division? That is like, I think that would equal 1. See, yeah, because it takes the floor. So cool. That's how we check the certain sub boxes. So what we're gonna do is we're gonna loop through all the rows and columns and basically assign them to specific sub boxes. And then once we have everything in their sub box, okay, we'll create a set. We'll create a set or a dictionary where the key is the sub box. The key is their sub box, which would be like 0, 0. And the value would be a set. And the set is like the unique numbers that are in that sub box. And if we are trying to insert something into the set and it already appears in the set, we have a collision and we return false right away. So that's going to be what our dictionary looks like. So let's just implement that. So let's say for row in range length of board, for column in range length of board 0. So now we're going through every row and column. What we're going to do is we're going to create a dictionary called sub boxes. The 9 boxes can have the middle as a key, then box around it as the values. The 9 boxes can have the middle as a key. What do you mean? What do you mean by that? Take a break. Some of our usual suspects aren't in today. Okay, we're gonna create a dictionary called sub boxes, and that's gonna be a dictionary. And what we're gonna do is we're gonna say like sub box row equals row divided by 3, and we'll say sub box column equals column divided by 3. So that gives us a unique like sub box that we want to access. Example 001. So that will give us the exact sub row we want to access. Then we'll say, now all we have to do is this. We have to grab the element. So element equals board row column. And then what we need to do is if elem is in, we'll take the sub boxes and we'll say sub box row, sub box column. So if the element is in there, we return false. Otherwise, we grab our sub box here and then we add, or we no longer add, but we say, oh yeah, here's when we can like make use of a default dictionary. So let's do from collection import default dicts. John, you're gonna like this one. Import default dict. This one is really good to use. Speeds up a lot of things. But what we can do is define a default dictionary. The key could be 0, 1. But how would we grab the key? So I'm thinking default dict equals set. So say subbox row dot add elem. Now what's happening? Expected true but got false. Row column. Where are we returning false? If element in subbox row, subbox column. The key. The 9 box can have the middle as a key. By middle, do you mean like this here? Yeah, you could do that. You could do that. What you could do is like, it would be a little bit more hard coded, but you could figure out exactly where the middle are and do that. That makes sense. You could do that, John. You can like just figure out exactly where these middles are and then just look around them using like -1 and +1 and stuff like that. I mean, that's a valid solution for sure. Like you should try out this question at some point when you get familiar with 2D arrays. I think this is good practice of using like sets. Okay, what's happening here? Where is it returning false? Columns. Don, what's the portfolio looking like now for your 1K to 10K? So the row is invalid. Why is it saying the row is invalid? For column in, if column in unique nums. If column in unique nums, print. We'll say column element, and then we'll say unique. Then we'll also print out the row. Or I don't care about that. Oh yeah, let's just print out the row. So we're at a specific row. We're at 537. Oh, because we're not ignoring the dots. So we need to ignore the dots. So if the column element, so what's happening is it's each dot, it's returning false on the first dot or the second dot that it's seen. So we gotta ignore those. If column dot continue. So that's how I would handle that case. And then for this case, I'll say if the element equals dot again, continue. And then lastly, over here, if the element equals dot, I'll continue as well. That should work. Nice. Now submit. Cool. 83%. DT, what's up? What's up? So that's how you use Sudoku. How you solve. That's how you check if a board is valid. But this is a hard LeetCode question where we actually now need to write a problem to solve a Sudoku puzzle for real. So to do that, a Sudoku must satisfy all the following rules. Let's see. What we can do for this is now essentially what we need to do is fill out the board so that it works and then return back the board after it's filled out. So pretend that we have an example like this. Let's see. And our goal now, so we have code that is able to check if it's a valid Sudoku. And what I want to do is actually copy this function because I know I'm going to need to use it for actually solving Sudoku. So I'll just copy over that code, is valid Sudoku, and then collapse it. So now when we're given a board, we can tell you if that board is true or false. And our goal at the end of this now is to return this 2D array, but actually have the result. Where'd it go? Let's see. So zoom out. This is it comes like this. This current. And then at the end, actual, we want it to look like this. So what we could essentially do here is we can just start trying to fill in the Sudoku puzzle and then backtrack. Have I ever got this in an interview? I got something similar. I got this one called Connect 4, and it was basically no, not Connect 4. It was it was Connect 4. I basically had to figure out all the possible ways that a Connect 4 game could end and print out those states and then print out how many different states could be generated from a Connect 4 game. So it's pretty much the same algorithm, but a little bit more simple. So what we're going to do is we're going to loop through we're going to try to like place different elements. So for here, we're going to look at what can we place here. We'll try 1, right? Then here, we'll try 2. We'll try 3. We'll try 4. We'll try 5. But we'll automatically see that we already broke the rule where we have 2 elements in one row that's 5. So we can't really do that. So we'll try 6. And then we'll see 6. But 6 breaks this column. On this question, you can set an attributes of the board for the sub. What do you mean by attributes? And yup, I actually got asked this for. Or I mean not this, but the Connect 4 thing. But we see 6, that violates this column. So we try 7, that validates like this row and this column. So we try 8, that validates again, or that validates this again. So we kind of like have to do a backtracking algorithm where we try all the different elements. We try for each element, we kind of try a specific number and then we validate to see if that puts the board in a back state. 3 is already in the row. Yeah, that's true. That wouldn't have worked either. So we would have placed that and then we would have tried 4. And essentially what we do is like every time we try something, if we're able to place it, then we continue. And if it ends up breaking something, then we backtrack to it and then we try something else there. And we pretty much do that recursively until we like fill out this. We pretty much go row by row, column by column, trying out all the different solutions until one solution works. That's the one way I know how to solve this problem. And I think you can, I'm not sure if you can speed it up. Yeah, I don't know if you could even speed it up. I think that's the fastest way to do it. But I'll look at the solution after. Yeah, you have to validate 3 possible things, row, column, and square. Yeah, you have to validate. That's what I did in the last question, was validate the row, validate the column, then validate like a subsquare. So rows are pretty normal way to do it. You just loop through one specific row and check for uniqueness using a set. Afterwards, you do the same thing for a column, looping through every attribute. Yeah, essentially. But let's see. you go through all the different columns and you do the same thing of just using a set to see uniqueness. And then for sub boxes, the one thing that I did was to calculate which sub box a row and column is I took the integer division divided by 3. So that would group all of these ones in 0, 0. Like this, that would group all of these ones in 0, 0. All of these ones in 0, 1, etc. And then that grabbed me my sub boxes. And once I'm able to grab my sub boxes, I could just check if there's collisions within a specific sub box. So that's pretty much what I did. And now I copied over that code of checking a valid Sudoku. And that's what I'm going to be using in my backtracking algorithm. So let's figure out how we're going to do backtracking. For this would be what is, since it's only max. I guess it's kind of constant. Yeah, I guess it's constant because we're limited. It's always 9 by 9. But how, if the board was unlimited, how you would calculate like the runtime is the branching factor. So how many elements are you trying at each position? So for us, we're trying about 9 different ones. So since we're trying 9 different ones, it would be like 9 to the n, I'm pretty sure. Because for each element, we're kind of creating like 9 different branches. Like we're trying out 1, we're trying out 2, we're trying out 3, we're trying out 4. And then for the next element, we're like branching off 9 more times. So that would equal of 9 to the n operation, if that makes sense. So you just, when you're looking at these exponential algorithms, you want to check out the branching factor. Like how many subproblems does it divide into? So what we're going to do is we're going to loop through every single one of the rows and columns, and then we're going to try to place different elements on each of the dots. So what we're going to do is for row in range, we're going to do some sort of backtracking algorithm. So what we're going to do is for row in range, let me think this out. How are we going to do this backtracking algorithm? Let's just try to loop through the rows and columns first for I in range length of the board. That goes through the rows. For column in range. Yeah, but anyways, like what's 9? Since n here is kind of like how many, since n is not, it is fixed because it's 9 here. It's basically, this algorithm is basically 9 to 81. That's probably a massive number. 9 to, it's constantly that big number. So let's loop through for column in length of board 0. Now we're looping through all the different rows and all the different columns. We'll say if the board row column is not equal to, if the board row, we also need to check if it's valid and solved. But essentially, we're going to loop through every row. We're going to loop through every row and every column. And if, what I'm going to do is I'm going to create a set of all of the elements that are blank and that we need to like possibly, like that we need to try to fill in. So let's make a list of blank spaces, and that's going to be a list. So if the board of row column is equal to a dot, we'll add that row and column to our blank spaces. That should give us a list of all of the blank spaces for us to do our backtracking algorithm. So what do we have here? So 02 is empty, 03, 05, 06, 07, then yeah, 1, 1. Okay, everything looks good there. Now what we're going to do is we're going to define like a backtracking algorithm. And there we're going to be given a board. We're going to be given a row. And we're going to be given a list of blank spaces. And then we're also going to be given we're given the board a blank spaces. And then we're going to be given an index. The index is going to tell us which blank space that we're going to try to fill. So first we're going to try to fill the zeroth row in second column. Then we're going to try to fill the 0th row in third column. And this index is going to tell us exactly like if we solved it. So what we're going to do is we're going to pretty much, for all the backtracking, we wanted to find a base case. So how do we know we reached the end? We'll basically say if the index is equal to the length of blank spaces, that means we've already used up all the blank spaces. Then that's our base case. Return self dot is valid. So yeah, essentially, if we reach the end, we want to see if it's valid. So that's going to be, we're going to pass in the board here. So that's our base case. For our regular case, and I can try to speed this up, this algorithm faster if it doesn't work, but we'll try to loop through all the digits from 1 to 9. 1 to 10. That will give us all the ones from 1 to 9. And what we're going to do is we're going to get the current row and current column from the blank spaces at the current index. So we're gonna basically do a backtracking algorithm where we call backtrack. We're gonna pass in the board. We can't really use asynchronous or any threads or anything like that, because like if pretend we had one thread filling this sub thing out, and we had this one filling this one out. I mean, let's see. That might work because these don't affect each other that much. But if we have one thread filling this out and one thread filling this one out, it's not going to speed anything up if we use threads, because everything kind of is linked to each other. Like if I make a decision over here, it affects everything here, affects everything here, and affects like over everything there. So I kind of will need to, and if I have a thread processing this, any decision will affect here and affect there. So they're kind of stepping on each other's toes. So usually threads will speed it up if the things that are processing could be processed independently. Where am I at? So I'm going from the board. I'm taking the blank spaces, and then we're gonna like try to fill in the 0th index. So for I in range 1 to 10, what we're going to do is we're going to take our board. We're going to say our current row, current column, like equals, we'll do string of that specific candidate. We'll say digit. So we're going to try anything between those in that column. And then what we're going to do is we're going to, let's see. We're going to say if, let's see, we're going to backtrack. So usually in backtrack, like you want to place an element, backtrack, and then place another, or like remove that element. So what we're going to do is we're going to place the element which is the current digit. Then we're gonna go do self.backtrack. So we're doing a recursive algorithm. We're gonna grab the board. We're gonna put in the blank spaces. And then what we're gonna do is we're gonna take the index plus 1 because we want to fill in the next one. So we'll just store result here. We'll say if anything actually worked, if result is true, then we just return true in our backtracking algorithm. Otherwise, we remove that element and we try the next element. So let's turn that back into a dot because that didn't work. So we want to try the next digit there. So we put a dot there. Let's see, what do we have here? Yeah, we remove that element. So if any of them return true, then that works. Otherwise, the worst case scenario will return false. So if index equals length, then we just check if it's valid. But we also want to be checking if it's valid every time. So we want to do if we do if valid. If it is valid is false, return false. Otherwise, here that means this will work true. So this is kind of the base case, or when this is the base case, like when we get to the very bottom of the recursion, and this is just like when we want to early stop. Let's see. Let's try running it. Backtrack. Solution dot is valid. Wait, where's it? Backtrack self is valid. So I'm just converting that. Let's see if this works. Okay, that worked. It might be really slow. We might time out. Oh, time limit exceeded. But we're able to get it to work on this one case, and how I can speed it up is probably speed up the way that I'm verifying. Like, I don't need to verify this whole thing every time. It's kind of slow. Let's see, how would I do this? Let me think about it. Any ideas in the chat? Let me try. So we're looping, we're grabbing all the blank spaces. I think I might be validating way too much. Is valid. So I think what I can do is yeah, that's one way. Only look through for numbers that aren't already in the first box. Yeah, let's see. What I can do is instead of checking is valid every single time, what I can do is we can create a, let's see. We can create a dictionary of rows unique, and then we'll do default dict set. We can do calls unique, and then we could finally do not just calls unique. We can do pretty much, we can do calls unique, sub box unique. So what we're gonna do is, like, for row and column, we're gonna do the various checks. We're gonna say if we're gonna grab the specific element equals board row column. So we already know the row, we already know the column. Let's just grab the sub box that we're in. So we just need to grab the sub box here. So we'll do the various checks. If the element is in, we'll say row's unique, and then we'll grab the row, return false. Or, yeah, we just return. Wait, we don't even need to, we're just doing this in place. We don't even need to. Nice, let's get it. Alex, where are you from? That's hype, man. You got this. Lock in. The winter is like the perfect time, honestly. So if element is in row's unique row here, what we're gonna do is, if we already seen that element in that specific row, return false. Otherwise, we'll just add it to the set. Dot add false, or add the element. So we'll do rows, columns, rows, calls. Then we'll do, yeah, collect that bag. Alex, where are you from, and like where are you trying to apply? So we do rows, columns, and we do sub box. So if element in calls unique, so we're gonna grab the specific column, and we're checking if the element is already in, like there's a collision, we return false. Otherwise, we add to the unique columns, or we add to the unique set for that column, that element. And then finally in the sub box. So in the sub box, we'll say if the element is in sub box unique, and then we'll grab the row column, or we're gonna say sub box row and column. If the element is in sub box, we return false. Otherwise, we'll just add here. Dot add element. So now we're verifying like as we go, and then now we're gonna pass in just these different sets. So essentially what I do is every time I place an element, like if I place like a 7 here, I'm just gonna check the current row I'm in and the current column and here. I don't need to be checking like all of these other columns and all of these other rows. So we'll speed it up by a little bit, but we'll see how that works. I'm just fixing up the valid, like the way that we check if something is valid. So we'll do, how long has this stream been now at this point? Cool, only 53 minutes, not bad. I'll get back on the advent of code. I just wanted to take a break from it, but I'll get back on it on probably tomorrow. Rows unique. Columns unique. Then we do sub box unique. So now we're passing these into our backtracking algorithm. So we'll just capture these parameters here as well. So where's this? So now we're able to do a backtracking. So essentially what we're going to do is when we place, let's see, we'll try to place if element. So we have a digit. Oh, now we need to know what row and column we're in. Okay, current row, current column. Yeah, we'll see. He's in Vancouver right now. So what we need to do is for every digit that we're gonna try to place, we're gonna go see if we can place, can we place, or can we place in row, can we place in column, can we place in sub box? So to do that, I feel like we just need to literally copy this code over. I know it's not the nicest piece of code, but it will probably work. So we take the current row, the current column, and we say we're already given the digit. If the digit is in the current row, then we continue. If the element is in the current column, then we continue because we don't want to use that. What's my opinion on CS50X? What is that, the Harvard course? I like that course. I did that course. I practiced a bit of that course before, just for fun. That's actually a pretty good course. I like how Harvard teaches, because you actually have to do a lot of assignments, and then you send those assignments and they actually mark it. I actually did this and it's pretty good. If you're new to programming and want to learn and actually want to learn like hands-on stuff, you should try this out. And also, I feel that having, like, you can add it onto your LinkedIn, and having things on your LinkedIn like different certificates really shows that you're willing to learn outside of on your own, and that's pretty important for anybody in the industry. So if element is in current row, what we do, if element sub box, unique sub box row sub box, call continue, or sorry, not return continue, literally just continue. If it hits any of these, yeah, it's a lot of work. But if you don't know anything about programming, you're starting from scratch, I would suggest literally, like, it takes time to get good. It takes time to get good. So where are we at? We're checking if the digit is unique in the row, if it's unique in the column, if it's unique in the sub box. If it's not one of those things, we want to continue. And then we'll like place the element. And then after, what we're gonna do, we're gonna say if, we're gonna say digit equals string. We're going to turn the digit into a string. So here we'll place the digit, but at the same time, we're going to also update the row's unique, and we're going to add the digit. Then we'll do the same thing for columns. And then we'll add the digit. And then we'll do the same thing for the sub box. Dot add digit. And then from there, we'll want to remove the digit. I think that'll make it a lot faster. What happened if? See. If the digit is in unique rows, continue. For I, let's see, add and remove the digit. Let's see how the board progresses in this backtracking algorithm. Then we're going to remove, we actually don't need this is valid. That was kind of made our algorithm slow. So we pretty much only printed out one board output. Why is that the case? For digit, blank spaces index. For digit, wait, now I need to debug this a bit. That's crazy. Is where did they ask you that? Was it a fintech company? Let's see. What's happening here? Why am I dipping out already? Return false, return false. Okay, let me read over my code. So I'm looking for if the board equals dot, then we append a space. Oh, we have to continue here. Where's is valid? Calls unique, backtrack. Okay. Hopefully this works. Hopefully this passes. Please. Nice, we got it working. Let's go. That was a little bit faster than my last submission. What's my last submission? How fast do people get it? What is this? So the last time I did it was a backtracking algorithm too. And how do people solve this usually? So, yeah. They use a backtracking algorithm as well. Basically means put a restriction. Okay, they do the same thing of like capturing. But the way they do it is a bit different. They capture like a box index instead of capturing like a box tuple. Yeah, and like like I was mentioning, it's like 9 to the 9 or 9 to the 81, which is like some big number. I don't know. I don't know why mine was so slow. This one looks slow too. And more code. But yeah, that's pretty much how you solve this question. Let's see. Still have some time. Maybe I'm going to hop into the advent of code. Actually, I don't know. Maybe I'll take it easy today. I'll be back on advent of code on day 14. But mostly in this live stream, I just want to show live. And what's up, Jay? I want to answer the question live of how we solve 2D matrix problems and things like Sudoku and spiral matrix. I want to show Sudoku. Spiral matrix is also interesting. That's another video for a different day, I guess. But yeah, this just hopefully I went through like my thought process on how I work with these. And now you know how to solve valid Sudoku. You know how to do a backtracking algorithm. So yeah, I'll catch y'all on the next stream. Tomorrow I'm going to be streaming. Probably I'll be streaming Advent of Code Day 14 because I've been lacking on this. But cool. See y'all in the next stream. Peace out.